In this video, we're going to look at the relationships between the different properties of gases. So the properties we're going to focus in on are the pressure, the volume, the number of moles of the gas, and the temperature. And so the first thing I want to do is just kind of let you listen to this little video here that sort of has an animation and some narration with it. And then we'll come back and kind of summarize what they've told you in this video.
Consider a gas-filled container that has a movable piston. It is exposed to an atmospheric pressure of 1 atmosphere. Click on one of the buttons to see animations of how temperature, pressure, or the number of gas particles. You can increase the pressure by adding a weight on top of the piston. Let's add a weight that will increase the pressure on the top of the piston to 2 atmospheres. As the pressure on the gas increases, the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the pressure of the gas equals the external pressure on the piston, which is 2 atmospheres. The volume occupied by the gas will be half its original volume. You should see that the volume is inversely proportional to the pressure. V is proportional to 1 over P. Adding a proportionality constant K, we can write volume equals K divided by pressure, or pressure times volume equals K. This relation is known as Boyle's law, which states that the volume of a fixed amount of gas is inversely proportional to the gas pressure at constant temperature. As the pressure on the gas decreases, the volume that the gas occupies increases. The volume that the gas occupies will continue to increase until the pressure of the gas is equal to the atmospheric pressure on the piston, which is 1 atmosphere. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature of the gas increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the temperature of the gas. We can write volume equals K times temperature, where K is a proportionality constant. This relation is known as Charles' law, which states that the volume of a fixed amount of gas is directly proportional to the gas temperature at constant pressure. Note that as the temperature is doubled at constant pressure, when the Bunsen burner the volume that the gas occupies, the temperature of the gas decreases, and the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the temperature of the gas equals the external temperature. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature is raised, the average velocity of the gas particles increases. Thereby the frequency and intensity of collisions of gas particles with the container walls increase. Pressure, which is defined as the force exerted per unit of surface area, will clearly increase as the frequency and intensity of collisions increase. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Note that as temperature is doubled at constant volume, the pressure exerted by the gas when the Bunsen burner is removed, the temperature of the gas decreases. The average velocity of the gas particles decreases, thereby the frequency and intensity of collisions of gas particles with the container walls decrease. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Gas particles are entering the container. As the number of particles, or equivalently the moles of gas increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the number of moles of gas. We can write volume equals K times N, where N is the number of moles of gas and K is a proportionality constant. This relation is known as Bhagat Rose Law, which states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas. In this animation, the moles of gas particles is doubled, and correspondingly the volume occupied by the gas is doubled.
Okay, So in kind of looking at that, he talked about Boyle's law. The key thing to remember is that Boyle's law relates pressure and volume, and that those are inversely proportional. And then Charles' law relates temperature and volume, and they are directly proportional. And again, you're holding all the other variables constant when you're just examining two variables at a time. And then Gay-Lussac's law relates the number of, or relates the pressure and the temperature when the number of moles and the volume are held constant. And those, the pressure and the temperature, are going to be directly proportional. And Avogadro's law relates volume and the number of moles, and again, holding temperature and pressure constant, and those are directly proportional. So if we look, and there's a separate video that covers this, but if we put all of those relationships together, we get the ideal gas law, which is PV equals nRT. And hopefully from your math classes, you will realize that the variables that are on opposite sides of the equal sign in this relationship are going to be directly proportional. So there's volume and temperature, volume and moles, pressure and temperature, pressure and moles. Okay, and then the variables that are on the same side of the of the equal sign are going to be inversely proportional. The key one here being the pressure and the volume. Okay, inversely proportional. So we can use the ideal gas law, okay, whenever we are looking at a situation where our conditions are not changing. So we have one gas and we know three of the four variables, and we're solving for the fourth one. And so if you check out my other video, I do one specifically on calculations with the ideal gas law. But in this video, I'm going to focus on the situation where we have conditions that are changing. And you could memorize all the different gas laws and then apply them to whichever situation works with the problem that you're looking at. But there is kind of an easier way to do that. And because basically what we can do, and I'll show you kind of where this comes from. If I say I have condition one, like the gas at an initial condition. So if I'm going to rearrange the ideal gas law. So if I rearrange the gas law, I get that PV over NT is equal to R. Okay, R being our gas constant. And so since R is a constant value, if I have an initial set of conditions, right, okay, that's going to be equal to R. But then if I change and have a second set of conditions, okay, I can set that's going to be equal to R. And so since they're both equal to a constant, they are indeed equal to each other. And so that's where this equation comes from. And the way that you can use this is there's one equation that you need to remember, and then all you have to do is anything that's being held constant for the problem that you're looking at, you're just going to mark that out, and what you'll be left with is the equation that applies for that problem. Whether it's Boyle's law or Charles' law or Avogadro's law, you'll end up with the right equation. And so we're going to scroll down, and some of these again these problems are in the other video, which you can see the ones that I'm scrolling past. These all have up above this last one here. Okay, so these are all one set of conditions. But now when we get to this one right here, all right, in here we have a 2.5 liters, so my volume is 2.5 liters, and my temperature is 25 degrees Celsius. And remember, you're going to Always with gases, you're going to convert that into Kelvin because the relationship applies to the Kelvin temperature. And then it wants to know, well, what is the volume if I raise the temperature to 100 degrees Celsius? So again, plus 273, so 373. All right, so I do P1 V1 over N1 T1 equals P2 V2 over N2 T2. And in this, I'm not changing the moles. Those are constants, they go away. I'm not changing the pressure, okay? And so that leaves me with V1 over T1, so 2.5 over 298 is equal to V2, which is my unknown, over T2, which is 373. So solving that, V2 then is going to be equal to 2.5 times 373 divided by 298. So I get 3.13 liters, which again, thinking of that, we know volume and temperature are directly proportional. So the answer would make sense. If I increase the temperature, I would expect my volume to increase as well. Okay. All right. So let's look at, we'll just kind of skip down to a couple different problems. So here I have a pressure of 2 atmospheres and a temperature of 25 degrees Celsius. So that's going to be 298 Kelvin. And it wants to know what will the pressure be if the temperature rises to 300. So that's going to be 573 Kelvin. All right. So again, P1 V1 over N1 T1. It's P2 V2 over N2 T2. All right. So again, I'm not changing my number of moles. In here, it's in a can, so my volume is staying the same. So I have P1 over T1 equals P2, which is, that's what I'm solving for, over T2, 573. So I have 2 times 573 divided by 298. So 3.8. And again, pressure and temperature directly proportional. If I raise the temperature, I would expect the pressure to increase as well. Okay, so let's scroll down and, well, the next one has multiple things changing. So let's look at, here I have a volume of gas. So V1 is 0.180 liters. My P1 is 0.8 atmospheres. And my T1 is 29 plus 273. So 302 Kelvin. And it wants to know the temperature if I change the volume to 90 milliliters. So I want the units have to be the same between, it doesn't matter what the units are. So this is not like the ideal gas law where volume always has to be in liters and pressure always has to be in atmospheres, but your units need to be consistent. So V1 and V2 have to be in the same units, P1 and P2 same units, T1, T2 same units. Okay, so I'm going to convert that to liters. So that's 0.09 liters. And then my new pressure is 3.2 atmospheres. And it's wanting to know what will my new temperature be. Okay, so here's P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. All right, and the moles are the only thing held constant, so we'll mark those out. So I get 0.8 times 0.180 liters over 302 Kelvin is going to be 3.2 times 0.09 divided by T2. Okay, so that gives me, let's see, 3.2 times 0.09 times 302. So I have 86.976 equals 0.8 and 0.18, 0.144 T2. And so T2 then is going to be equal to 604 Kelvin. So you can work other examples, but they basically all work the same way. So the key thing is recognizing that you have conditions that are changing, and so you're going to use this equation, marking out anything that is being held constant in the problem that you're